All right, for this video, we are simply going over the practice exam for our first unit. And everybody in class has the exam sitting in front of them, so that's why we don't have them up on the board. Starting off, reading the first one. Armando lives on one end of a street with a newsstand on the other. At this point, I'm going to stop. One of the pieces that is very helpful in geometry, since this is a class that is very, very much about shapes and pictures, if you're not given one, you should always try to draw one. The picture will help a lot of people remember what they need. And so, just based on that, can you create a picture based on what we just read? Yes. Armando lives on one end of the street, there's a newsstand on the other. We've got Armando and the newsstand. Just based on that, what topic should we be thinking about? We've got a segment, so obviously we're thinking about the stuff that we know about segments. Armando picks up newspapers at the newsstand and then delivers them to 14 equally spaced houses on his way back. Okay, so we're looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Of course, the last one had to change it. Okay, I guess it's got to stay yellow. He travels from the newsstand to the first house, then delivers a newspaper to each house. At the end of his route, he continues down the street and goes home. Find the distance from the last house to Armando's home. All right, so here's what we're noting. The distance from the newsstand to Armando's home is a grand total, based on our table, of how much? Right? 340. Obviously, then, from the segment addition postulate, all of these pieces combined have to be a total of 340. The distance from the newsstand to the first house is 30. The distance between each of the houses on his route are 20. And then we are asked, what is the distance from the last house to Armando's home? We got to add them all up. So since it's just repeatedly adding 20, we're just going to multiply it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 times 20. Or 13 times 2. Or 13 times 2, then adding a 0 on, we'd wind up with 260. So all of those are 260. And we got to put the other 30 on, which gets us up to 290. The last amount then, subtracting that off, we've got 50. We have our answer. We're done. Now I'd like to ask you, without the drawing, how many of you guys would have looked at that and said, oh yeah, clearly I've got to multiply 13 times 20, add it on to 30, and subtract it off? You're probably not going to have that. This is why drawings are so incredibly important. Even if you make a mistake with the number crunching, if you have an accurate drawing, at least it demonstrates you understand the problem. By itself, that's a good thing. You always earn points for the things that you do well. Understanding the problem and creating a good, accurate drawing, that's a good thing. You gain points just for that. Okay, so that was number 1 in the numeric response section. Then we'll go to number 2. A satellite completely orbits Earth in 216 days. Determine the angle through which the satellite travels over a period of 12 days. Okay, so we're going to start off with the Earth. And you like how it's all nice and blue? It's got lots of oceans. Yep. And then yeah, we're just drawing a circle. All right, so here's what we need to consider. How many degrees are in a whole circle? 360. And so what we're noting then is 360 degrees for the entire circle. That's how long it's going to take for the satellite to orbit the Earth. How long does it take to orbit? 216 days to do the full orbit. One of the pieces that we could then note, the problem asks us, what degree is it going to be over a period of 12 days? We can set this up with 12 days. Whoa. 12 days. Come on, man. I need my pen. There we go. 12 days. And we're searching for the variable. Now that we have our proportion set up, we can simply solve it with cross multiplication. Multiply the first diagonal, 216 times x. Multiply the other diagonal, 360 times 12. That's 4,320. And then when we divide that out by 216, that will give us 20 degrees, and thus we have our answer. We're done. And our next section is based on matching with vocabulary. So we're going to start running through number 1. A shape that results from the transformation of a figure. Which one is that? That is the image. Remember, we discussed pre-image gets moved with a transformation and goes to an image. It's before, middle, and end. Pre-image is the beginning, transformation is the middle, it does the changing, and then image is the ending value. Thus, what we're noting in this instance, since the shape, this is the shape that result is telling you the end, that's where we finish. All right, the second problem, the original figure in a transformation. That's choice H, that's the pre-image. Moving to number 3. A transformation across a line. That one is a reflection. You ought to remember when we were discussing reflections, our initial description was that there is an axis of reflection that you flip across, and things get flipped across at that 90-degree angle. That's our characterization. This description of a transformation across the line is referring to the line that we flip across. Continuing to number 4. A change in the position, size, or shape of a figure. Well, if you change a shape, or if you change a figure, what is that? That's a transformation. So far, the only transformations we've examined will move a shape. They don't change size. They don't change the shape. They only move the position. We will look at things that change the size, like dilations. We will look at things that change the shape, like vertical or horizontal stretches. But those are a topic that we'll be working with down the road. We haven't got to them yet. Number 5, rotation. A transformation in which all the points of a figure move the same direction and the same distance. That's a translation. It's like sliding your notebook across the table. They all go the same direction, they all go the same length. And so that one is choice A. Continuing further to number 6, we have match the vocabulary again. One of 2 sides of a right triangle that form the right angle. Okay, it still wants to draw those circles for me. So we're looking at a right triangle the right angle, one of the two sides that make up the right angle. Those are legs. And leg is choice G. Number 7, the number of non-overlapping unit squares of a given size that will exactly cover the interior of a plane figure. If you start covering something up with squares and asking how many little squares does it take to cover the shape, that's area. It's exactly what area is, the amount of space on the inside, where we consider space to be the number of squares. Continuing to 8, the side opposite the right angle. So what's the name of this piece? Yes, that is our hypotenuse, which is choice D. For problem number 9, the distance between two endpoints of a segment. That's nothing more than the length. The length of a segment is the distance between the endpoints. Finally, number 10, a segment drawn from a vertex that forms a right angle with a line containing the base. That's referring to, we'd have a triangle. If we draw down at a right angle, that piece is referring to the height of the triangle. And so height is letter C. It's phrased the way it is because of obtuse triangles. If we have to extend this outward to get that 90 for the height, this is the line containing the base. That's why it's phrased so weirdly, so that it also incorporates the obtuse triangle picture. Moving to the short answer section. Question number 1. Looking at the picture of the plane, name 2 lines.
AR, WT.
AR and WT. There's something wrong with that. And everybody's coming up with and starting to draw with their hands. That's good. Remember, these pieces, without anything drawn, that refers to lengths. That's the distance AR, not the line AR. If we want a line, we have to draw the little line on top of it. If you were to put down these pieces and just call it here, that would be a segment. Don't forget the arrows. Now, CJ, you made the comment, why wouldn't we put down C? You only need 2 points to name a line. If you wanted to, you could have said ACR, because those 3 points are all in a line. They're all collinear. You could have said this, and it would have been absolutely the same thing. It's just a different, correct way to refer to that first line. Same thing with WT, since C is the center. If we had simply said WC, this is another correct way that we could have referred to the line WT. You only need 2 points for a line. Just make sure that you're not accidentally using the same line twice with the 2 different names for it, though. Okay, continuing to question number 2. Draw and label a pair of opposite rays, FG and FH. What are opposite rays? And I'm starting to see some hand signals with people saying like this, and they're pointing in opposite directions. That's exactly what they would be. We could draw our first ray, FH, going toward the right, using the same point F as a common vertex, going in the exact opposite direction, we could create the ray FG. And we're finished. We have everything we need. All right, the question just got asked, does it matter if the h is on the right or the left? If we had drawn it like this, we don't have a problem. Because they're still opposite rays, but f is still in the middle. Where we would encounter a problem, if we messed it up and put it like this would not work. Because then we don't have the ray FH. We would not have the ray FH. It would start at the endpoint, go past F, and we know that those are not the same thing. F did need to be the middle point, but it doesn't matter where the G or the H were. You may also recall that when we were drawing these pieces and discussing them in class originally, we said that it's common to draw them horizontal. They don't have to be horizontal. You could have done them vertically, straight up and down, or on some kind of a slant. That would work too. Okay, number 3. Sketch a figure that shows two coplanar lines that do not intersect. Well, first of all, what does coplanar mean? Coplanar tells us that they're in the same flat surface, the same plane. And so that's where I'm going to start. I'm going to draw a plane to begin with. And so I'll continue by drawing a line. And here I'm going to draw another one. Tell me what you think about my drawing.
Beautiful.
That's wrong. In particular, the directions told us have lines that do not intersect. Well, we could look at my drawing and say, hey, my picture doesn't cross, but lines go on forever. They're going to cross. If we actually extended it like a line should, they will cross. So I don't meet the criteria. In order to fix it, to make sure that we have lines that don't actually intersect, we need to do what you told us to, CJ, and draw them so that they look parallel. Now, I'm not going to grade, you don't get graded based on your ability to have an absolutely perfect drawing. This isn't an art class. I don't expect perfection out of these. But your sketches need to be good enough that I can understand what it looks like. And if it looks like they're going to cross, I'm going to assume that they are. If it looks like you're trying to draw parallel, we'll assume that's what you're trying to do. Yes, sir. Now, there is still another part to this problem that I haven't read yet. Sketch a figure that shows two coplanar lines that do not intersect, but one of the lines is the intersection of two planes. So we already have one plane drawn. We're going to need to draw another one. Moreover, that plane needs to be passing through one of our two lines. All right, so how do we draw that? Well, I'm going to start by saying right here, oh, I wanted to change the color so people could see it better. Right here is the intersection of my two planes. I'm going to bring this one up and just draw it and say, here's the top part of my plane. But a plane is going to continue going down too. So what was our convention for drawing underneath a plane, where you drawing when you can't actually see it? That's where we used our dotted lines. To show that behavior, that it goes underneath, we would draw using dotted lines like this. And that's what we have. We have everything that we would need. Okay, continuing with the next one. Now, I'm not going to write down the entire problem, but I did want to write down this particular section of the directions. In part because we had something similar to this on our quiz, and people tended to struggle with it. So I want to make sure that we're very, very clear about this. This word bisect has a very clear meaning for us. What does bisect mean?
Split in half.
Split in half. So if we split or cut something in half, we could use that to create a drawing. No. Once again, I do not expect a perfect drawing. We're just looking for a sketch. The picture is there to help us understand the problem. It's not the answer by itself. And so I'm going to come through and create a sketch, putting it down to help us understand what's going on. And I've got those pieces in the wrong order. It's A, B, C. The angle is bisected by a ray BD. By actually creating the drawing, it can help us understand what's going on. Typically, when we encounter a problem that says bisect, one of two things are going to go on. First of all, we know that these two angles are equal. One type of problem that pops up with bisecting is creating an equation where you say these two angles are equal to each other. That's how you make the equation, which you will then solve. Keep in mind, bisecting can also happen with segments. We could have a similar problem where we say we're bisecting a segment instead of bisecting an angle. The ideas are the same. A midpoint will do the same thing. A midpoint cuts them into equal halves. Well, the second type of problem is based on the segment addition postulate. Because these angles are the same size, the overall angle is twice as big as the small one. And so a second type which can arise is saying double a small angle to equal the overall big angle. And these equations only work because of the word bisect. We know that it was cut into equal sized pieces. Well, continue reading the directions. Which one of these do we have? Which pieces are we given? The problem continues by saying the measure of angle ABD. So A over to B over to D, that's giving us a small angle. The measure of angle DBC. D to B to C. Which ones were we given? Does it fit the equation in the black or the equation in the blue? It's fitting the black because we were given the small piece and we were given the small piece. That's how we can identify which one we want to do. We're looking at the pieces that we're given, checking which relationship actually works. Thus, to build the equation, and I'm going to erase to create some space here, we have the measure of angle ABD is 7x minus 1. The measure of angle DBC equals 4x plus 8. Now we have to solve. We'll put our x's together, combining the like terms. Add to undo that piece of subtraction. Dividing by 3 to isolate the x further. We have our result that x is equal to 3. And I'll pause here waiting for people to catch up with the notes. But I'd like to caution you, we are not done. Go back and check your directions. What did the directions ask us to get?
Is it 6?
Find the angle ABD.
The directions,
Is it 12?
the directions asked us, find the measure of angle ABD. They did not say find the value of x. We've done a lot of good work, but we're not done. Within the directions, the measure of angle ABD, which we actually do want, the directions tell us that is 7x minus 1. So substituting that in, 7 times 3 minus 1, that's 21 subtract 1, which equals 20 degrees. And now we're finished. Making sure that we actually read the directions. Always read the directions. They tell you exactly what is expected of you. They tell you exactly what is wanted. Continuing further, we can read the directions and notice that 5, 6, and 7 are all related to the same picture. And I'll do a quick sketch here simply because I want to be able to write on it and reference some pieces. Okay, and so in question number 5, we are asked, what kind of angles are 1 and 2? Are they adjacent, a linear pair, or neither? So which kind are they? Adjacent?
Linear.
These are going to be adjacent angles. And we can recognize them as adjacent because they share a side. Basically, they're like apartments that share a wall. That's how we can think of adjacency. They're right next to each other, sharing a wall. But when we actually put them together, those two by themselves don't create a straight line. Since it's not a straight line, it's not linear. Progressing to problem number 6. Problem number 6 asks us about angle 1 and angle 3. And so when we draw those out, we have angle 1 and angle 3. Where are they? Adjacent, linear, or neither?
Linear.
Sometimes students will look at that and see, well, they are making a straight line right here. And because they're making a straight line, a lot of times students will say they're linear. But be careful about that because it's not correct. In order to be a linear pair, they need to be adjacent. A linear pair would be something like here, where the two angles come together, and it's only two angles side by side that create the line. In this problem, we have this angle number 2 that's kind of like a hole in it. Since we do not have adjacent angles, we cannot call these adjacent, and we cannot call them a linear pair. This is neither one. Question number 7 then gives us if we combine angle FAC and angle 3, what kind are those? This one does form a linear pair. They are adjacent, sharing a wall. They do form a line. Therefore, they are a linear pair. Progressing forward with question number 8. And number 8 gives us a billiards table where we have the ball. And again, I'm not trying to have a perfect sketch, but we've got a trick shot coming where we have angles 1, 2, 3, 4, 5, and 6. A billiard ball bounces off the sides of a rectangular billiards table in such a way that, I'm going to use my tick arcs to help record things, angle 1 is congruent to angle 3. Angle 4 is congruent to angle 6. Angles 3 and 4 are complementary. Based on that information, and also knowing that the measure of angle 1 is 26.5 degrees, we want to determine what is the size of angle 3, what is the size of angle 4, what is the size of angle 5. So which ones can we get right away? Immediately, because these are congruent angles, 1 and 3 have to be the same. That instantly gives us 26.5 degrees here. And then because 3 and 4 are complementary, we know that 26.5 for angle 3 plus the measure of angle 4 has to add up to 90. So simply subtracting off 90 subtract 26.5, that'll give us 63.5, telling us the size of angle 4. Chaining this together further, 63.5 is angle 4, angle 6 is congruent to angle 4, so both of those have to be 63.5. And now we want to figure out, lastly, how big is angle 5? Well, there is a piece here that you must recognize, and the directions don't tell us it. You need to recognize that we have, on this right-hand side, 3 angles forming a straight line. Together, those 3 angles have to add up to 180. And so we would need to recognize 63.5 plus the measure of angle 5 plus 63.5. That's going to give us a grand total of 180. And frankly, I don't expect to see people write that equation down in purple. I'm writing it down to show you the way that I'm thinking about it. What I expect most people will do, instead of writing it out like this, I assume most people are just going to say add up the 63.5 together, or just double it, which would give you 127. And so I expect to see something probably more like the bottom line, or I might wind up just seeing people write it out like here, showing their work of 180 subtract 127. Even if you're not writing down and creating the equations, if you're recognizing these components, we'll still be able to identify our pieces and get a 53-degree angle, finishing us off. Question number 9 asks us to find the circumference and the area of the circle. Pay attention to the directions. They tell us, use 3.14 for pi. We will not use the pi button on our calculator. We're told not to do that. The directions say, round the answer to the nearest tenth. I expect them to be rounded to the nearest tenth. That's what the directions are telling us to do. Don't ignore the directions. They're telling you exactly what you need. So, for this particular problem, what is the formula for the circumference of a circle? It is 2 pi r. What is the formula for the area of a circle? It is pi r squared. I do expect you to know these circumference and area formulas. I don't expect you to have every single formula for the entire world memorized, but these area formulas for basic shapes, rectangles, triangles, circles, these building block shapes that you get used all over the place, you do need to have those ones down cold. Make sure you know your perimeter and area formulas for rectangles, triangles, and circles. All right, so putting them in, we had 2 pi, and the radius we can see in our picture is 4 feet. So what is 2 times 3.14 times 4? 25.12? That would be wrong. The directions told us round to the nearest tenth. Make sure you don't forget to follow the directions. That's going to be about 25.1. don't forget the label. 25.1 feet. We're told it's feet in the problem, don't forget that. For area, pi times the radius squared. Putting those together, we would have 50.24. And when we round that, we have 50.2 feet squared. Don't forget the label. For question number 10, we are given there are 4 fruit trees in a square backyard. Each side of the square is 30 feet. What is the distance from the apple tree to the plum tree?
30.
It's not a distance of 30. We have to keep in mind, since this is a square, we have a right angle. That absolutely creates a right triangle. That's perfectly set up for Pythagorean theorem. And so to use the Pythagorean theorem, we'd have legs squared plus legs squared equals the hypotenuse squared. Substituting in the side lengths that we know, 30 and 30, trying to figure out the hypotenuse length. So 900 plus 900, that gives us c squared is 1800. Taking square root, it's exactly the square root of 1800. But since the directions told us to round to the nearest tenth, we can put this into our calculator. The square root of 1800 is about 42.42. 42.426. Well, rounding that to the nearest tenth, that's 42.4 feet. Don't forget the labels. Don't forget to follow and do what the directions tell you to do. Question number 11 is fairly straightforward. What kind of transformation is that? Visually, we can see it's a rotation. Describe that with arrow notation. ABC got moved to A prime, B prime, C prime. We're using the prime and arrow notation to describe how they got moved. Question number 12 gives us a picture. An animated film artist creates a simple scene by translating a kite against a still background. Write a rule for the translation from kite 1 to kite 2. Well, with a translation, we know that all we have to do is count. Visually, we can see that we're going to the left and up. Take a look at your picture and count how far over. How far to the left does it get slid?
6.
How far up does it get slid?
6.
That's our rule. We're done. Left 6 and up 6. Lastly, we've got this plane with some lines drawn. Name 3 collinear points. What does collinear mean?
EGRN.
All in a row, all on a line. So when we look at them, R, G, and N all fall on the same line. We're done. And that finishes up everything we needed for our practice exam.